Okay, so back to the ring. This is a metal ring, and I've tied a string to it, and I'm pulling due north with a force F1. I tie a second string to it, and I pull at a 45-degree angle below the whatever you want to call it, horizon. I pull that way with a force F2, and then I need to know how to exert another force, F3, in order to keep it in equilibrium. In other words, what angle do I need and what force do I need? Now I'm going to specify. This guy is going to be 10 newtons of force, and this guy is going to be 7 newtons of force. So what angle do I need to balance this thing out? And this becomes a two-dimensional problem. Let's go ahead and draw a free body diagram. 10 newtons this way, 7 newtons at an angle of 45, and unknown force at an unknown angle. So what we have to do is we have to componentize these two forces, and we have to componentize them into an x component and a y component. The other force that needs to be componentized is the unknown force, which will be componentized into a y component and an x component. And we have to look at them separately. So the x component of force 2 pulling to the right must be exactly equal to the x component of force 3, the unknown force, pulling to the left. That means that F2 times the cosine of 45 degrees must be equal to F3 times the cosine of our unknown angle. Well, this equation will not be solved because although I can put in 7 newtons times the cosine of 45 degrees and get a number for that, we have two unknowns on this side. So we're going to need another equation. I'm looking around for my calculator and I don't see it. This is all hiding under my cell phone. There it is. Let's just get this done. 7 cosine 45 equals 4.949, so 4.95. And that's as far as we can go using the x direction. But, however, and on the other hand, we can look at the y direction. Now, in the y direction, the upward pull of F1, which doesn't need to be componentized because it's strictly in the y direction, must be equal to the sum of F3 in the y direction and F2 in the y direction. Now, F1 is 10 newtons. F3 in the y direction is F3 sine theta. And F2 in the y direction is F2 times sine of 45. So doing a little bit of algebra, I'm going to substitute in what F2 is, and I'm going to move this term to the other side. We're going to have 10 minus 7 sine 45 equals F3 sine theta. Okay, so that's going to be 10 minus 7 sine 45. Now 7 sine 45 is the same as 7 cosine 45, so that's 4.95. So 10 minus 4.95 equals 5.05. And that's equal to F3 sine theta. And now I have two equations, both of which have the same two unknowns, this one and this one. So we could pull a trick to solve for these things. One trick is to solve for, I know a trick that works every time. Here we go. Divide the two equations by each other. We're going to take the 5.05 equals F3 sine theta, and we're going to divide it by 4.95 equals F3 cos theta. Do you see why I'm doing this? I'm doing this because the F3's cancel, and the remainder is tan theta. So I'm going to take 5.05 and divide it by 4.95, and that's 1.02. And that's going to equal tan of theta. So I can get that theta equals, second function, tangent of the answer, theta equals 45.5 degrees. Actually, that's 45.6 if I round it correctly. So I now have half of my answer, and then I can plug that in somewhere else to get the other half of my answer and find out what F3 is. We can go ahead and do that. I'm going to use this blank area over here. 4.95 equals F3 times the cosine of 45.6. So that would mean that 4.95 divided by cosine of 45.6 is going to equal F3. And let's see, 4.95 divided by cosine of 45.6 is 7.07. And now I've figured out exactly how hard and at what angle I have to pull in order to balance these two known forces. That's a fairly complicated problem, but all we did is we drew a free body diagram. We componentized, and then we wrote equilibrium conditions for both the x and y dimensions. Wound up with a system of two equations, two unknowns, and bludgeoned it and stole its money. Okay, let's keep going. So far, everything's been in equilibrium, but that's not always the case. Sometimes things are moving. So let's take a box and let's specify that it has a mass of 5 kilograms, and it's just floating in space. And so we're going to hook a rope up to it, and we're going to pull it this way, and we're going to pull with 10 newtons of force. Now we can figure out what acceleration we're going to get on this box. Now I know this box can't be in equilibrium because there is an unbalanced force, a clearly unbalanced force on it. So now we can just plug these things in. The net force is just 10 newtons because there's only one force. Oh, now I'm including units in my equations. Great. And that's 5 kilograms times A. So A must be 10 divided by 5, or 2 meters per second squared. Very simple situation here. Could this get more complicated? I certainly think it could. What if we had two opposing forces? What if we had our 10 Newton pull this way, but there was a 6 Newton pull to the other way on a 5 kilogram box? Well, now F net equals m times A, and F net is going to be a positive 10 minus a 6, 10 in the positive direction, 6 in the negative direction, and that's going to equal 5 times A. And it looks a little cleaner when I leave the units off. Just remember to put the units in at the end, and that'll help you out. So here we got 4 equals 5 times A, or 4/5 equals A. 4/5 is 0.8 meters per second squared. So a significant decrease in the acceleration when we have a force that is pulling in the other direction. Here's one that gives people a problem. Here we go. We're going to have a 3 kilogram box attached by a rope to a 5 kilogram box, and we're going to pull this way at 14 newtons. I don't need even numbers, okay? And I'm going to ask two questions here. First thing I'm going to ask is, what is the acceleration of the system? And the second thing I'm going to ask is, what is the tension in the string between the two boxes? Now, your first thought might be that if this is 14 newtons, then the tension here will be 14 newtons, but I'm here to tell you it's not. Okay, and what we can do is we can draw a free body diagram for each of these guys and come up with a system of equations that lets us solve this. So the free body diagram for the second box is a simple dot with one force on it, just the tension in the string. But the free body diagram for the front box has 14 newtons pulling this way and T pulling back this way. So the behind box, I'm sure that's not the right word for it, but the last box in the chain is this diagram, and the first box in the chain is this diagram. So we have two separate things to do. We can, by the way, kick the training wheels off the bike. Do you have to write F net equals m times A down each time? No, not if you start getting good at this stuff. What if we just wrote down the upshot of it? That is to say that T equals m times A, so T equals 3 times A. That's as far as we can go because we don't know T and we don't know A. But over here, our net force is 14 minus T, and that's going to equal 5 times A. See, this is a 5 kilogram box, so we use 5 here. This is a 3 kilogram box, so we use 3 here. And this is another equation that we have. I'll tell you what we could do. This T looks like it could substitute very quickly right in there. So 14 minus 3A equals 5A. So 14 equals 8A. And 14 over 8 equals A, which is going to be, what is that? 7 over 4, 7/4, which is 1.75. And from that, we can back substitute into this thing. T equals 3A equals 3 times 1.75 equals 3 times 1.75 equals 5.25 newtons. So now I know the acceleration and the tension by doing 2 free body diagrams, 2 separate Newton's second law, and a system of equations that allowed me to solve for 2 things. Now, some of you might have noticed something as we did this, and that is that when we did this step right here, we wound up with an 8. This kind of looks like F equals ma as applied to the whole thing, treating this entire system of 2 boxes connected by a rope as one object. That object's mass would be 8. That object would have a 14 Newton force on it, and then we could find the acceleration. And that's actually a strategery. That's actually a technique that is used. It's called the system trick. The system trick to solve complicated objects is to treat the object as if it is one big thing, maybe with some internal forces, and then look at that as one big blob and look at the external forces on it, use that to find the acceleration. And then given that acceleration, you can go in and find the tension. We could find the tension once we find the acceleration simply by drawing this free body diagram. So I want to show you some other systems that can be solved with the system trick or straight ahead, but I need to look at the clock because we're getting close to time here. So far so good. So far no questions. So far all okay. Okay. Going back to the, so here's something that often freaks kids out quite a bit. We're going to put a box on top of a frictionless surface. We're going to put a pulley on the corner, and we're going to have another mass here. So this is going to be, let's say this is a mass of 5 kilograms and this is a mass of 3 kilograms. And we're going to ask, what is the acceleration of this system and what is the tension in the string? Now, if you do this using the system trick, this is what it looks like. To do the system trick, you draw a dotted line, inside of which is a 5 kilogram mass attached to a 3 kilogram mass. And you ask yourself, what forces are making this thing move? Well, the only force that's making this thing move is the weight of the hanging mass. The mass on the table is supported by the table. So we have the weight of the hanging mass, and the weight of the hanging mass is the mass times g. So what acceleration will we have? F net equals m times a. The only force is m times g, the mass of the small guy, times g. And then this mass here is the mass of the whole shebang-a-bang. So that's going to be 8. So I guess I should have put a number in for this one. That's bad planning. So this is 3 times g equals 8 times a. And that means that a will be 3/8 g. 3/8 of 10. God, I only wish I could come up with a number for that. I guess I'll just do this. I'll just do 3/8 times 9.8. 3 divided by 8 times 9.8 equals 3.675 meters per second squared. Now I've got an acceleration. If you want to find the tension inside, now we have to abandon the system trick and just draw a free body diagram for the trailing mass. That's the easier one. because it only has one force on it, where tension is pulling it forward. And so in this case, F net equals m times a would be the net force is the tension, and that would be just the mass of the trailing mass times the acceleration, which we know is 3.675. And that's a tension of 18.375 newtons. So that would be the way to solve this using the system trick. The system trick is a good imagination thing, but it's really not good at finding the tension, having to draw a second free body diagram. If someone just asks you for the acceleration of the system trick is awesome. If you don't do the system trick, we have to draw a free body diagram for the mass on the table, and we have to draw a free body diagram for the mass that's hanging. And we say, okay, this is a tension pulling to the right, and this is a tension pulling up and m times g pulling down. Then we have to come up with a system of two equations. T equals m times a for this one is T equals 5 times a. I'm getting a ding dong. I got a ding dong there. Is that a ding dong from you? No, it is a ding dong from the email. Okay, cool. And then over here, we're going to have a mg minus T equals m times a. By the way, why didn't I take T up as positive? Because if T to the right is positive, that means that this entire system moving this way has to be considered positive. You need a consistent coordinate system. So we're forced to make this downwards direction positive, which is the direction the system would move in anyway. That's what I'm trying to say. So here we have mg is 3 times 9.8 minus T equals 3 times a. And now I have a system of two equations. It's really good to take this T and substitute it in here. So we have 3 times 9.8 minus 5 times a equals 3 times a. Once again, moving this to the other side, we have 3 times 9.8 equals 8 times a. And now we can go ahead and find out that a equals 3/8 of 9.8. And we know that that is 3.675. Substitute that back in here, and you have T equals 5 times 3.675. And we get the same result we did before, 18.375 newtons. So whether we draw two separate free body diagrams and have two equations, or whether we do the system trick, we're going to get the same results. And I don't care which one you use. I will do examples in class both ways. And in fact, in the homework, on my homework solutions, there is one problem that I did both ways to show you how it works. Okay, this has been a crash course in how to solve physics problems. And I'm going to make an assignment of your homework. I was supposed to do that this morning, but I got balled up in a